Now, fortunately, when we analyze algorithms, actually not too many different functions arise. And actually, that property allows us to really classify algorithms according to their performance as the problem size grows. So that's what we'll talk about next. So the good news is there's only these few functions turn up about the algorithms that we're interested in. We can craft things that have other functions, and there are counterexamples to this. But really, a great number of the algorithms that we consider are described by these few functions that are plotted here. When we're talking about order of growth, we're not talking about the leading constant. Normally we'll say the running time of the algorithm is proportional to n log n. That means we think that our hypothesis is that the running time is tilde c log n, n log n, where c is some constant. And in these plots, these are log-log plots that really give a good idea of what's going on. If an order of growth is logarithmic or constant, it doesn't matter how big the thing is, it's going to be fast. If the running time is t for, say, 1,000, then for 500,000, it'll be pretty close to t. If it's linear, if its order of growth is proportional to n, then as the running time, as the size increases, the running time increases correspondingly. And the same is true almost if it's n log n. So those are the algorithms that we strive for. They scale with the input size. As the input grows, so grows the running time, and that's a reasonable situation to be in. As we talked about when we talked about union find, if it's quadratic, the running time grows much faster than the input size, and it's not feasible to use such an algorithm for large inputs. And cubic is even worse. So what we find is for many algorithms, our first task is really simply make sure it's not quadratic or cubic. And these order of growth classifications actually come from kind of simple patterns in terms of the code that we write. So if our code has no loops in it, then the order of growth is going to be constant. If our code has some kind of loop where the input's divided in half, and so binary search algorithm's an example of that, then our order growth will be logarithmic, and we'll take a look at that analysis. But if you do the doubling test, it grows almost linearly. If you have a huge input and you double the size, it's still going to be, I'm sorry, not linearly, constant, just like if it's constant. You'll hardly notice that log n. If you have a loop where you touch everything in your input, then the running time is linear, proportional to n. So a typical example of that would be find the maximum or count the number of zeros, our one-sum problem. A very interesting category is the so-called n log n algorithms or linear arithmetic algorithms. And those are the ones that arise from a particular algorithm design technique called divide and conquer. And the merge sort algorithm, which we'll talk about in a couple of weeks, is a prime example of that. And then if you have double for loops, like our two-sum algorithm, that's going to be time proportional to n squared, as we saw. That's quadratic. Or triple for loop, like our three-sum algorithm, that's going to be cubic or time proportional to n cubed. For a quadratic algorithm or a cubic algorithm, the doubling factor is 4 or 8. As the input size double for a cubic algorithm, the running time goes up by a factor of 8. And that's the kind of calculation you can do in your head while waiting for a program to finish. There's also a category of algorithms whose running time is exponential. And in those algorithms, n doesn't get very large at all. And we'll talk about those at the end of part 2 of the course. So these are some practical implications of the order of growth. And I won't really dwell on this too much, except to come back to the point that the algorithms that we're really interested in that can solve huge problems are the linear and n log n algorithms. Because even now, a quadratic algorithm on a typical fast computer could only solve problems in the tens of thousands, and a cubic algorithm only in the size of thousands. And nowadays, those are just not useful because the amount of data that we have is more like the millions, billions, or trillions. That fact is becoming more and more evident as time wears on. In ancient times, we'd have some discussion about whether a quadratic algorithm might be useful, but the situation gets worse as time gets on, so we need better algorithms. To illustrate the process of developing a mathematical model for describing the performance of an algorithm, we'll look at a familiar algorithm called binary search. The goal is that you have a sorted array of integers, say, and you're given a key, and you want to know, is that key in the array? And if it is, what's its index? And a fast algorithm for doing this is known as binary search, where we compare the key against the middle entry. In this case, if we're looking for 33, we compare it against 53. If it's smaller, we know it's in the left half of the array. If it's larger, we know it's in the right half of the array. If it's equal, we found it. And then we apply the same algorithm recursively. So let's quickly look at a demo. So we're looking for 33 in this array. We compare it against the middle entry in the array, 53, and it's less, so we go left. So now we can concentrate just on the left half of the array. Now we look in the middle of this half, that's 25, 33 is bigger, so we go right. Now we concentrate on the right half of the left half, and we have a smaller subarray. Look at the middle, 33 is less, so we go left. And now we have only the one element to look at, and we found our key 33 in the array, and we return that index 4. If we're looking for something that's not in the array, we do the same process. So say we're looking for 34, it's going to be the same. Look in the left half, look in the right half, look to the left of the 43. Now there's only one key to look at, and it's not 34, so we say it's not there. So that's binary search. So here's the code for binary search. Binary search, although it's a simple algorithm, it's notoriously tricky to get every detail right. In fact, one paper claimed that the first bug-free binary search wasn't published until 1962. And even in 2006, a bug was found in Java's implementation of binary search. Just an indication of the care that we have to take in developing algorithms, especially for libraries that are going to be used by millions of people. So here's an implementation. It's not recursive, although often we can implement this recursively. And it's just reflects in code what I described in words. If we have to find whether keys in an array, we use 2 pointers, low and high, to indicate the part of the array that we're interested in. As long as low is less than or equal to high, we compute the middle, and then we compare our key against the middle. Actually, it's a 3-way compare. It's either less or it's greater. Or if it's equal, we return that mid-index. If it's less, we reset the high pointer. If it's greater, we reset the low pointer, and we keep going until the pointers are equal. And if they're equal and we haven't found it, then we return -1. And it's easy to persuade ourselves that this program works as advertised by thinking about this invariant. If the key's in the array, then it's between low and high in the array. All right, so that's a program that you're probably familiar with. Let's look at the mathematical analysis of that program. And this is a theorem that we're going to prove. We usually, we won't do a lot of proofs, but this one's worth doing. So it says that binary search uses at most 1 plus log base 2 of n compares to complete a search in a sorted array of size n. So we do that, set up the problem by defining a variable t of n, which is the number of compares that binary search is going to need for an array of size n. And then we write down a recurrence relation that reflects the code. And what the code does is it divides the problem size in half so that t of n is less than or equal to t of n over 2, plus, depending on how you count what the compare is, think of it as really a two-way compare. So divide it in half by doing one compare. And that's true as long as n's bigger than 1. If n's equal to 1, the solution is 1. So that's a recurrence relation describing the computation. And so we can go ahead and solve this recurrence by applying the recurrence itself to the first term on the right. That's called telescoping. So if this is true, then we can apply the same thing to t of n over 2 and throw out another 1. And if this is true, we can apply the same thing to n over 4 and throw another 1, and so forth, until we get down to just 1, in which case we have log n 1s left. Now, this is a proof sketch. You might have noticed that this proof actually only holds if n is a power of 2, because we didn't really specify in this recurrence what we mean if n is odd. But it's possible to go ahead and, possible to go ahead and take care of that detail as well and show that binary search running time is logarithmic always. All right, so given that fact, we can develop a faster algorithm for threesum. It's a sorting-based algorithm. And so what we're going to do is we're going to take the numbers that we have as input and sort them. We'll talk about sorting algorithms next week. And we can get that done in time proportional to n log n, but that's not the main part of the computation. The main part of the computation is after the numbers are sorted, we'll go through and for each pair of numbers, AI and AJ, we'll do a binary search for minus AI plus IJ. If we find it, then we have 3 numbers that sum to 0. So we sort our numbers and then go through for each pair, do a binary search to see if it's there. So minus 40, 0, minus that is 40. We do a binary search that's in there. So we have one solution to the threesum problem. And do that for all pairs of numbers. Then a quick analysis says the order of growth of the running time is going to be n squared log n. You don't even need a good sort. You could use the elementary insertion sort, the first one we talk about. But the running time of the binary search for each of the pairs, each of the n squared pairs, or n squared over 2 pairs, we're going to do a binary search, so we get an n squared log n running time. So that's a quick example of how we can improve the performance. We can find an improved algorithm to solve a problem. N squared log n is much less than n cubed for large n. And so we're implicitly making the hypothesis that if we do this sort-based thing and use binary search, we're going to have a faster program. And sure enough, we can go ahead and run some experiments and find that whereas it took us 50 seconds to solve the problem for 8,000 numbers before, it's taking less than a second now. In 50 seconds, we can solve up to 64,000. So typically, we expect that better order of growth means faster in practice. But when it comes to examining the algorithms in detail, we can go ahead and do the tests and figure out which algorithm is faster. And certainly going from n cubed to n squared log n, we're going to expect that we're going to have a much better algorithm.